of course, was John's transition to the lab, as was in Netherlands some years ago. So some of our collaborators on the problem, Ting and Dian at IV Research, Kim from Imperial, Don Thursday and the student Chan from UMass. So these folks are all supported by the US UK ITA. So the ITA is ending in a month or so in some sense appropriate to kind of wrap this up. Also on acknowledge JITR, so I had some funding from JITR, so they were interested in the following problem. Have a known network and some matched event occurs, maybe EM false, and the whole part of the network gets taken out. How quickly can I refer services? How quickly can I infer topology? And so that's the problem they're interested in. I'm not going to talk much about that today. So the motivation is as follows. So network management is a difficult task. And it's much more difficult in a wireless tactical network where you don't necessarily know enough about what's happening in the network. So for example, why do you need it? You need it to reallocate resources. So resources could just be communication links, could also be computing services, could be mapping services, imaging services. Right? If this is distributed or a tactical network, I need to know the state of the network in order to do efficient resource allocation. And you can have all kinds of different things. Links may fail, even a lot of congestion on link, nodes may fail, other things can happen. If you want to be able to try and figure out what the state of the network is, but trying to figure out where these things are. So some of the challenges, so again, I'm talking about a tactical network, so I care about complexity. Okay? You are energy constrained, so you want solutions that are scalable. You want solutions that are low complexity. Of course, you worry about overhead. If the solution is going to create a lot of overhead in communication, then you have pretty much ruined what you try to set out to do. Right? So the other issue in a collision network is that you often work with partners, let's say US, UK, Afghan, but you have some trust between partners, but not enough. Which means that policy may tell you that you can do some things, you cannot do some other things. Right? So these are the challenges that we have. So of course, since we talk about networks, we'll use graph theory, we'll talk about estimation, so it is just inference, standard tools one would expect. So the key assumptions, one key assumption, I know the topology. So we have other work on topology inference, which is what John is saying, topology inference means, tomography means that you also infer topology. So here I'm going to assume I know the topology, and it's a bunch of other work, for example, some recent work, Novak's group had some work, Anima had some recent work on, which assumes that the graphs are sparse, the some structure, and from that is able to infer topology. So with JITR funding, we had some work with Tom Laporta, again on trying to infer topology. But I'm not going to talk about that today. I'm going to assume that I know topology, and I'm trying to figure out some properties of the links and nodes, so the up or down, some delay and stuff. So we can talk about different ways of doing this measurement. So right, one is direct or indirect. So the control, the ICMP gives you different techniques such as ping and trace. We often use them to figure out whether our networks are up or down, right? But typically what happens is in a collision network, these could be disabled, right? ICMP is not necessary to be on in every network. More importantly, if you use a trace log, you can have anonymous nodes, which is that they pass on the packet, the trace log packet, but they don't give you the node ID. So when you try to reconstruct stuff, you have a lot of ambiguity. So the indirect one is what we're going to use. We'll talk about that a little bit more. And I'll talk both about metrics that are additive, Boolean, and also the approaches that are either deterministic or stochastic, or something of a random process model for the deterministic. So the tomography problem is to infer the internal characteristics from external end-to-end measurements. And the blurb on the bottom is just to give the arbitrary of the problem, why is R interested in this? This is officially collision network and all that good stuff. So this is a one-slide high-level description of what you want to do. So think of this as a black box, so there's a blue thing shown out here. I want to understand something about the link metrics, this is a W1, W2. So think of them, for example, as link directs, right? I don't have direct access to those links. If I did, then the problem is obviously trivial. What I can do is I can inject probes, let's say from this node G, and I can measure the end-to-end part delay at node G. And I can do that for a whole bunch of end-to-end measurements. So I get some set of measurements, Q of W equal to C. So So Q depends upon what I'm trying to measure and how the link metric maps onto the path metric. So in the simple case of additive metric, you just get a linear algebra problem, right? It's just a sum. So the goal in tomography is you want to invert this problem. Okay? So given the function Q, given C, how do you find a W? So often the problem may be ill-posed. You don't have enough measurements, you don't have sufficient time, then what do you do? So we'll talk about that a little bit. So again, as I said, in the case of additive metrics, this is a simple problem. You get the matrix product of R and W, you know R, so you can solve for W, assuming R is open. Of course, there's a lot more to the story than that, and we talked about that quite a bit. This could be multiplicative, right? If I want to measure packet drop rate, then it's multiplicative plus length. Of course, it will take logarithms, and then you're back to a problem that you know about. It could also be Boolean product. So, for example, nodes may be up or down, links may be up or down. So the end-to-end path is up, so every node, every link is up, right? So then you get a Boolean problem out here, and that's a little bit more complicated, and we'll talk a bit about that as well. And then you could have other things such as maybe Q is the min function. I'm trying to find rate, for example. What's the rate on each link? So the end-to-end rate is the minimum of all the things on it. This is the high level thing of what I want to do. So I want to figure out how to settle this matrix on, how to invert the set of equations, how to do it efficiently. Okay, so I'm going to talk about, since the broad outline of the talk, I'll talk about additive links first, and then we'll additive work to the same, right? Talk to deterministic and then stochastic. If I have time, we'll talk about Boolean tomography. So that's the harder problem. So again, as a motivation for additive link metrics, could be delay, average delay, delay, average delay. It could be delay jitter. It could be traffic density. Again, as I said, it could be packet loss if we allow for logarithms. So assumption I'm going to make is that you only allow to use simple paths, right? So there's some work in the literature where you allow to use cyclic paths, i.e. you have loops in the your measurement. Most routing protocols do not allow for loops, so we're going to assume that you can only have simple paths. Because there are loops and problem is simpler, but most packets you can drop. So then that's an example of the average assumption. Okay, so just a simple example to say why the problem is solved. So look at this small example with 9 links and 6 nodes. Let's suppose your monitors M1, M2, M3, which means that I can send probes from M1 to M2, M1 to M3, M2 to M3. I'm assuming symmetric, so you can do it either direction. So you can enumerate all the paths, and I've done that out here. So the ones in red are the paths that go through other monitors. For example, this one goes from M1 to M2, but it goes to M3 and so on and so forth. Right? So there are a lot of paths out here. So even if I know the topology, the number of paths could be exponential. I think of a fully connected path. It's a very simple case, but you could have a very large number of paths, and they're not all independent. So first question, of course, is what is the complexity of trying to find n linearly independent paths, given that I have n links that I want to estimate. So going back to how do I determine this story? This was a full column map. How should I set this up? How many paths do I need? Where do I set the monitors? An example we'll see later is that if M2 is not a monitor, then the problem is simply not solvable. So it's always a question of where do I place the monitors and how do I make them? So monitors are expensive, right? So you want to have as few monitors as possible. And so that's the other thing we're going to look at. Okay. So very often when we think about graphs, we look at trees. Trees often give us a lot of insight. So let's look at some examples of trees to see if we get insight on how many monitors are needed. So this simple star graph, I have n links, and clearly I need n monitors. Right? All the leaf nodes are the monitors. The center node need not be monitored. That's enough for me to infer all the link nodes. Okay, so let's think of a line graph. Again, I have n links, but here every node has to be monitored. And this has to be monitored because it's not. There's no way I can infer about this length. This degree 2 node has to monitor, otherwise I can only get the sum of these two. I cannot get them individually. Right? So clearly all degree 1, degree 2 nodes have to be monitors. What can I say about other ones? Another simple example. Here I have 6 links. I need only 5 monitors. And again, the leaf nodes are the monitors. So I need these 2, I need these 3, And with these three monitors, I could do that measurement, and that measurement, and you get three equations, three independent equations, three unknowns, and you can estimate all the time. Binary tree, well, of course, all the frequency and monitors are roughly half. So this example we saw before. So supposing that the inner block is known, I know everything with this inner block, and I have 4 links and it is made of 2 monitors. So this problem cannot be solved. Right? So you can set up 4 equations. Right? I can get a measurement that goes from M1 to that link to that link to M3, one from here, and I have a cross from here to there, and so on. So you do get 4 equations, but the set up the matrix of rank 3, and you cannot solve for any of the 4 links in this case. So 2 monitors are not sufficient. So the question then is, how many monitors do you need, and how should I place them, and how do we understand such a problem?
So as we discussed, this is block process.
This is block process.
We don't allow sequential process.
So I'll talk about sequential later on.
No, because I could do props from a subset of the node that we make monitoring, get some information based on that, use it, and that actually can reduce the.
So, but here I'm trying to find the minimum to begin with. The minimum number of monitors, and then I need only n measurements. I think that's it. I'll talk to that later.
I have a feeling good because of sequentiality that we do better in some circumstances.
So that's definitely the case if the monitor locations are fixed, right?
But do I have to use all of them all the time? You said because.
So the inversion is that at the end, so it doesn't matter, right? In some sense, the density is not.
You said because you try to find the minimal one, right? You're covered.
Yeah. So, but if the monitor becomes fixed, then indeed you probably don't need to use all of them. That is more useful.
So what is your performance metric here? Do you want exact reconstruction?
Yes.
Well, not construction, inference of the property. You know the topology, right?
I know the topology, so I want to know the link metric. Let's say it's delay, right? So I want to know the delay on every link, all of them.
Exactly. So if you want,
So
for example, for one of them, you get a large network, you miss one of them. That's
Right.
right.
So I'll talk to partial later on. So right now, the first thing I'm assuming is that I want to know every link. And then later on, I'll talk about what can I do if I cannot do it.
For that problem, you have an exact model
For
the problem that we talked about.
For-
If I know the topology and I'm trying to find a failing one, then the method we use for the word space will have an exact.
where you don't know the topology.
No, I know the topology, but I'm trying to find a faulty link or not.
Okay. So I
And I
have
mean an
a,
exact tomography in the sense that we have integrals and random responses.
okay.
This we should compare notes.
Okay, so we have, as you might expect, we have things in terms of connectivity. K connectivity, we're trying to find faults and K plus 1, K plus 2, depending upon what kind of routing protocol. So if you have time, we'll talk to that at the very end. But that's more complicated than additive. Okay. So then, hopefully, topology will tell us more things about it. The first simple result we have is the following. So back to what John was saying. So suppose I'm given kappa monitors, the monitor locations are fixed. So the question I want to know, the question I have is, can I consider full rank matrix R? Enumerate all the parts you have. What can you do with it? Can you measure all the? Can you infer all the links on it? So we have. So first, of course, we saw that 2 monitors are not sufficient. Right? We saw the example before, and you can prove that 2 monitors are not sufficient in any topology other than the simple one where we have a simple. So the identifiable result is that this notion of the extended graph should be 3 vertices. So the extended graph is shown out here. I have the original graph G. I'm given my kappa monitors. I create 2 virtual monitors, M1 prime and 2 prime. I connect them to all the real monitors. So I added 2 virtual nodes. I added 2 kappa virtual links. And the extended graph has to be 3 connected. And why do you need 3 connectivity? You can see the reason for that in the next slide. You can show that if this GX is not 3 vertex connected, then it cannot identify all the links. So you have necessary insertion condition. And of course, you have old result of Hopcraft on measuring 3 connectivity. It's linear in the number of links. We know also the number of nodes, but that's less of a interest. So we can do the division. So given a placement of monitors, we can quickly figure out whether or not it's sufficient. So then, supposing it's sufficient, supposing the three vertex connectivity is condition holds, how can I set up path efficiently? So why is this important? So as I said earlier in that example, the number of monitor to monitor paths can be extremely large, and you want to choose n independent ones from that. Right? So of course you could try to enumerate them, but again, that would take a whole lot of time. So the idea is to create one more extended graph. So we put this other node R connected to those two virtual nodes and to one of these monitors. So then so the new construction adding R still leaves that original extended graph 3 vertex connected. By construction, there's still 3 vertex connected. So a good result from Menger, which is that if you have such a 3 vertex connected graph, you can find 3 vertex independent spanning trees. So why is that useful? So for example, I can find 3 vertex independent trees that go from B to R, right? So by construction, they have to go through the monitors, any 3 monitors. And it will not be repeated monitor because it's a vertex independent one. So I can get these 3 things like this. I can make measurements on S1 plus S2, S2, S3, S1 plus S3, and therefore I can infer the link metric on S1, S2, S3. Because S1 need not be a single link, it could be a composite link. The single link I've done. Supposing it's a composite link, then that means I have another node out here on this segment, and I can repeat the same thing. Again, I find the composite link into S1, which means I can now figure out the value of the link metric of UV. And you can keep doing this. So again, all you need is these 3 independent spanning trees you constructed, and from then you can figure out all of this, all of it. So this tells us how to set up the path, and then also tells us how to estimate the link metric given this. So then, we have not talked about monitor placement. So let's talk about minimum monitor placement. So here I'm assuming, conceptually to do the following, right? I could take 3 monitors, place them at M2 scale locations. That's for 3 connectivity. If it doesn't get satisfied, I have one more. M choose 4 locations, and so on. I keep doing this till I get 3 vertex connectivity. So that's of course computationally expensive. So we can do something simpler. So first you can look at simple words. So first is say, if I have a leaf node, that must be a monitor, right? For example, this one. This must be a monitor because otherwise I cannot infer this link metric HS. Degree 2 nodes must also be monitors. An example over here is this KJT, because if I don't have a monitor here, there is no way I can tell the values of those 2 links separately. All I can get is the sum of these clusters. Then you can, so then for the result we had that we need at least 3 monitors, 2 are insufficient. You can make similar arguments about subgraphs of 2 cut vertices, subgraphs of the single cut vertex. For example, this one, this subgraph of single cut vertex. If I remove this thing is disconnected. And in this case, we must have at least 2 monitors inside. Why? Because even if I know the rest of the graph, that means this is a virtual monitor. If I don't have 2 real monitors inside, I will not have enough measurements, enough independent measurements. So these are some simple rules, and it turns out we can show, proof is complicated, we can show that this is sufficient, that this is Gaussian sufficient. This algorithm will give us the minimum placement of monitors. Now there are possibly many equivalent monitor placements, but they give us one with the minimum number of monitors.
When you are in wireless, you have to be careful, right? Because you don't have links here.
So then we can talk about multiclass, and
right.
If I have some time, and then I'll talk about multiclass. So that's one where not enough work has been done.
Right, because I mean, this argument won't hold if the links are quote unquote wireless connections.
So, and we can do better.
Because you have, that's a fact.
Yeah, we can do better. And example of that.
Thanks.
So the multiclass case, not enough has been done.
Right.
Okay. So the time complexity of all of this is linear and number of unknowns, right? The number of unknowns is the number of links. So identifiability is linear in L. Monitor placement is also linear. So is the path. So path connection is a little bit more expensive. It's V times L, not V plus L, but still it's linear in L, right?
The size of the network is where V.
So these are the, so we talk about links, right?
Yes.
So
but the size of the network is represented here by V.
The V, right? The number of nodes is V, and L is the number of links. Right? Yeah. So of course, in it could have B roughly equal to L and the network is parts. So the matrix inversion also turns out to be linear only because of the way we set up the path, right? There is 3 independent paths. Just because that type of construction we are able to get order N rather than order N cube, which is what one would normally expect. Let me show some examples earlier. So we first looked at random graphs and then looked at some ISP topologies. So here we looked at Edward-Shanian random geometry graphs and Barama-Sharber graphs with parameter m equal to 5 for the BA. Holotropy loads in every case, and we set the parameters so that we get roughly the same number of links in every case, 700, in this case, 730 or so. Kappa bar is the number of monitors required on average because the 100 various things, right? So 2 things to observe immediately are that for ER and BA, that is for the value of PV and for ER, these are very, very well connected. So you need only 3 monitors. The graphs you start with are already 3 vertices connected, so which is good, right? The Barama-Sharber was robust 5, which means every time you introduce a new node, you're making 5 connections. So of course you are ensuring that 3 vertices connected, except for the starting code graph, which may or may not be 3 vertices connected. Okay, so what do we compare this with? So we could, so this is a path construction. So I could say I find the optimal monitor placement. Then we use a random walk to figure out the different path. So start the monitor and do the random walk, then hit on the monitor, take out all the loops. I keep doing this until I have enough independent paths, and then again do the matrix inversion. In that case, I would have to do actual matrix inversion because I will not have this nice property. So
what is the time comparison for those?
So the time comparisons, I'll show you 2 things here. So this is for construction and this is for inversion. So this is for the our algorithm, this is for the random walk base, this is for the matrix inversion.
So, okay. So between ER and BA, they're very similar.
Between, yeah.
In almost all methods.
For ER and BA, yeah, for this case, yeah. Again, kappa is split, so it's a very nice graph, right? So you can see a lot of these things. So of course, the random walk method doesn't always give you full rank path because of uncertain time. There are lots of paths, you may not find all of them in certain.
If you look at graphs that they have higher sparsity than these.
So we are
because
looking at
there you're going to see the real difference. Right?
Yes. So in some of the ISP ones, I'll show the next page, above networks are faster one, more difficult. And even this one, we've done in later on simulation study where you change the diameter of RG and make it fastest one. It's possible hard.
Yeah.
You have fewer choices.
Yeah. You can collect less information.
So of course you get the speed up for path construction, you get speed up for matrix inversion, again because the nice property. So one disadvantage of the method we have is that the paths may be much longer. So this is what a random walk uses, this is what our construction uses. So in some cases comparable, but in some cases so the BA, it's quite a bit of difference. So of course you can remedy this in multiple ways. The monitor placement is minimal, but it's not unique. You have different choices, so one could presumably look at different monitor placements, try and find the one that uses the minimum path time. We haven't done that, but that's something one could potentially do. So then again, similar set of simulation results. These are a bunch of ISP topologies. Of course, these topologies are now annotated. We got some rocket fuel a few years ago. I got annotated one. But the observations are similar. Right? Again, you get a good speed up for path construction versus a random walk based one. The matrix inversion is also easier, again for the same reason we talked about. And as in the case of the random network, the average path lengths are much larger in our case. Not so much more here than in the random case. Right? Except a couple of cases, 13.975. So it's bigger, but it's longer, but not much longer. Okay. So then let's talk about the question that we asked, which is what if I cannot identify all the nodes? So why would this happen? This could happen for multiple reasons, right? One is that given a placement of monitors, it does not search to the 3 vertex connectivity. So then I know that I cannot identify every link. Then the question, of course, is can I identify any link, and how many links can I identify? And so an algorithm will do that. And again, as you'd expect, given what we did before, it's based upon doing decomposition of the graph into biconnected and triconnected components. Each triconnected component, you look to see whether they have inner virtual monitors or real monitors. If they're free, you can identify. So you can do this recursively, you can figure out all the links that you can identify, and the complexity is again linear and non-complex. So then the other problem, of course, is that in some of the topologies, the minimum number of monitors you need is quite large. Right? So here, to show you the IIT topologies, this is the minimum number of monitors you need with our algorithm. This is the number of nodes. So you have one. So this is a good case, I guess, 90 of 600. But this one, for example, about half. This is about half. This is about half. Right? So in many cases, many of the nodes need to be monitors, and this is because of John similarly, these are somewhat sparse. So many of these ISP networks have a core subnet that is well connected, but then there are a lot of other subnetworks that are loosely connected. So of course that means, the sparse parts of the network, you need to have more monitors.
And the number you give in your work is that optimal?
The K I have, the last column is optimal. It's a simple part problem. If you allow to have cycles, you have to three connected, you need only one monitor. And of course, there the path lengths are much longer because it covers longer cycles. Okay. So then the question is, how do I place this K monitors optimally? So of course, I could use this one and say that I'll look at every placement of K monitors. So I have M choose K different placements. For each of them, I could figure out what the number of identifiable links and choose the best. But we can do better. Right? And we can do better in some caveats. So the greedy algorithm that is optimal if you have two connected graphs. It's not optimal. The complexity again is linear in L. There's a small n cube term out there. So n sub t, the number of tri-connected components in the graph that you have. Typically that's much smaller than the number of vertices that you have. So a complete graph is a different story, but a complete graph is always reconnected, so you don't have to worry. So again, we have solutions that are linear in L, and said can do the real graph and figure out how many monitors to be. So here's a simulation run for this for three different ISP topologies: E-born, XLS, and EBONET. And I'm showing you the optimal on top. So the optimal is the enumeration. Right, so I look at every possible placement of K monitors and then figure out how many links I can identify. And then this is the greedy algorithm, and then there's some variations on time to speed of some
of the two axes.
So axis here is the fraction of nodes that are monitors. So kappa divided by the and this is the fraction of links that I can identify.
Okay.
So once I reach the minimum kappa, so this is flattens out. So interesting thing first of all is that it's roughly linear below that, and our GMMP greedy algorithm is close to optimal in most cases, not exactly in most cases. So even for practical topology, the greedy algorithm works well. So then next we talk about dynamic topology. So far I assume that the topology is static. I continue to assume that I know the topologies, but I have a sequence of topologies. So I'm given capital T different topologies. I want to do monitor placement across all of them because I want to do some kind of optimal. So different things one can do. So one can look at a one-shot placement. So the basic idea here is that if I have a three-vertex connected graph, adding links does not destroy the problem. Adding links will still use the original graph.
Dynamic here means what?
Sorry?
Dynamic topology means what?
So dynamic here, so maybe across a set of topologies is a better set of links.
So, but dynamic means that I add or subtract nodes?
No, it's only links.
Links, yeah.
Only links. Yeah.
The nodes are the same?
The nodes are the
But
same.
I may have links appear and disappear.
Links appear and disappear.
Okay.
I have different topologies, different set of topologies can be better. So one-shot placement is based on the idea that densification does not destroy the three-vertex connectivity property. So if I can solve it for a small network, add links to it, I'll have to set the R matrix differently. I need more measurement. I don't need more monitors. So I create this base graph, which is basically the intersection of all the different topologies I have, and then I do monitor placement on that. So I like discrete components, you do monitor placement for each discrete component. If you isolate a node, that must be a monitor. And then it's easy to see that that placement will be adequate for the entire set of T topologies. And of course, if one of those T topologies require the same number of monitors as the base, then of course this is optimal. You cannot do it less, you do not do it. The other one is to do incremental placement. So I started, let's say, topology T1, I find out the minimum placement for that. Then I get topology T2, the question I ask is, how many more new monitors do you need? I'll keep what I had at the beginning and keep adding monitors. And so I get T1, T2, and then I get T3, I do the same thing. So every step, I get a new topology, I keep all the old monitors, I try and add the minimal number of monitors. So again, the complexity.
You need more in the second? In other words,
Yes, you will need more in the second.
in other words, if I add a node or a set of nodes, okay, not that the node is the same. But what I had before as monitor is not optimal for the biggest.
So
If I incremental in this sense, right?
Yeah, so the ordering becomes important. Right?
Yeah.
Because I could start with a good topology
You
and
may end up with more
Yeah.
than if you do it in one shot. So if you compare the one shot result versus the two-step,
Right.
you may have cases where the two-step gives you more.
The two will give you, unless it's three connected, in which case those three connected is that's good to have. So what we'd like to do is optimal joint placement, which is what is the minimum number of monitors I need in total, right? And so that works for all these topologies, and we, of course, it's simply hard to correlation it's a problem.
Sorry, what is the script have?
Script.
Scriptless.
So I'll come to that in a second, right? So script F comes about by we're trying to put this in a ILP formulation for our constraints. So the constraint could be, for example, if the three connected subcomponent, I need one virtual monitor or two virtual monitors. And so that's what you do for the decomposition. You decompose into tri-connected components. For each you say how many I need, so you can set them as a bunch of constraints. So F is the total number of constraints I have. For example, one constraint is all degree 1 of the monitors or degree 2 monitors. So the constraints themselves. So you get an approximation that's logarithmic. Okay. So let's look at some simulation results. So on the top, I'm showing you two different networks. One is the infamous San Francisco taxi cab data set. I think we had about 19 nodes in that. Measurements are taken every 10 minutes, and so in about 8 hours we had 400 topologies. The second is a tactical network that's based on the latest data, I think, from the young involved in CV learning activity. Right. So we had a Lakers exercise, and then ARL created a synthetic data set based upon that to mimic group mobility. So again, you have about 90 traces, 400 different snapshots. And so for these two different, they are different mobilities. Right? The taxi cab data set, the cabs kind of move independently. In the tactical network, you have subnets that move in tandem, not boxed out, but not too much variation. So you have subnetworks that are fairly stable topologies, so you have fewer topologies. And what I'm showing, so the x-axis here is the range, so this becomes communication range, i.e. Larger values, the range means you have a more and more denser network, so you should expect to have fewer and fewer monitors. And of course, you see that kind of there. And then these 5 bars, the first one is the one shot, then the incremental, the joint, which is the optimal, and then a refinement. The refinement is, we know that the one shot, for example, there are many monitors that are not needed. So we heuristic get rid of some of the redundant monitors, not all of them. They get rid of the complexity. But it gives a refinement, it gives you identifiability by reduce the number of monitors. And then a lower bound. So the lower bound basically is based on the fact that the number of monitors I need must be at least the maximum across the set of topologies. Right? So it's a lower bound specific to the set of topologies that we have, not as an algorithm. So of course, as I said, you can see that the trend, of course, is for tensor network, you need fewer monitors. The one shot doesn't work very well, particularly when you have.
But there is less difference between the methods in the tactical network versus the passive.
Yes,
And
because
the reason is,
right. So reason I got many subnetworks that are stable across time. So even though the network is moving,
okay.
the subnetworks
While
are
the
fine.
other case you don't have that.
In other cases, I don't have that. So yeah, so many of the monitor placements do not change. So that's what the talk matters.
Thank you.
So then here we look at a different thing. So here what you're saying is that so what if the given topology is incorrect? So I do the monitor placement based upon a bunch of given topologies. So in this case we have XY location. So let's suppose there's an error. Right? So we added, might expect that added because the noise is the sigma of the noise added to the location. So then the topology is not incorrect. Then you can look at the monitor placement and say, is it sufficient? If not, I need to add monitors. So what's the average number of monitors I need to add? And so that's shown here. Number of temporary monitors I need to add across time, but really it's about the number of snapshots. So the interesting thing in both cases is that you need to add very few monitors on average. And so in some sense the algorithm is robust. We don't have a theoretical reason for this, and of course I would caveat to saying there's only the density that's important. The network is very densely connected. We have some errors in topology, it doesn't matter.
You also see from the tactical that after a certain distance,
Right.
it doesn't change
It
much.
doesn't change. All the five
So
networks are
there's
the
a
same.
sweet
Here's
spot
one
in the distance that you actually can get everything
Right.
with a very small number.
With a very small
Versus the other one where it's not.
Yeah. And then these other two ones are, so what if I cannot afford to have a bunch of monitors with monitors all the time? So this is a cost, right? To make a node a monitor costs you something. So maybe you don't want to label nodes with monitors all the time, which means maybe keep percentage them as monitors persistently, and then you activate some other nodes as monitors as needed. So cost for activation. So the top graph shows you what is the total number of monitors I need, keeping a certain number fixed as persistent. Right? And the bottom one shows you the number of changes. So this is more important because this is how many node change, how many status changes do you have? It's really close to the cost of activation. And of course, as you can imagine, as you have more persistent monitors, you have fewer changes that you need.
Are you concerned at all about keeping your monitors up too much time so you run out of energy or not?
Okay, that's a very good question. So I don't have the results in this one, but the paper will look at the following problem, which is, so I have three topologies, and each of the topologies is active for different periods of time, right? And then that goes back to how long should different nodes be monitors, what's the cost of doing
Because you may not need them to be honest.
You may not need them beyond all the time, right? Exactly. Yeah. And then of course that's even harder problem. It's still NP, so obviously it's still NP, and yes, some good issues to solve in that. So this is a recap of what we've talked about so far, and just for the additive case. Right? So you look at different things. The first one was, what are the topological conditions to ensure identifiability, to ensure that a full rank or measurement matrix might exist? How do we do the path construction efficiently? How do we do the inversion efficiently? And then optimal monitor placement. How do we deal with dynamics? How do we deal with the case where the partial identifiability? And for all of this, what we saw was that everything is linear and the number of unknowns at the end. So at least the complexity is here. So now I'll talk a bit about stochastic approaches. So I'll talk a little bit about everything seems to be connected, but
very capable. That's the Microsoft solution.
Yeah, that didn't seem to work.
Yeah, here it is. Yeah.
Okay.
Works.
So I'll talk about the stochastic case next. So this is where I have some random variable model for the link matrix. Again, I talk to two things. So one is the packet loss tomography. So the packets are getting dropped with some probability P sub L on link L. How do I infer that value? Second thing is packet delay variation. So the delay is random variables, got some variance. I don't know the variance. And I want to estimate that, the sigma L squared on link basis. And of course, you do the standard thing, right? I have the unknown parameters, measurements, write a likelihood, I try to maximize the likelihood, and then estimate the error. Okay. So we can write the likelihood function explicitly in these two cases. So y is the path. So this is piece of y is all the links in the path. So x is a binary variable indicating whether or not the path is successful. And so we can write this easily, right? The per path likelihood for this case and the per path likelihood.
This assumes independent losses from path to path, right?
I'm sorry?
Independent losses from path to
Independent
path.
passes from link to
Losses
link
from
and then
link to
from,
link, sorry.
and yes, so the next step, the next slide is from path to path. Yeah. I mean, if you know the correlation model, you could set it up and you could just absolutely. Okay, so you have these things. So in the deterministic case, probing the same path multiple times doesn't add any value, right? It doesn't change the random matrix. It doesn't give any additional information. But that's not true in the stochastic case. Some paths may be more informative than others. So the question is, how often should I probe different paths? So what if I given a budget for a number of probes, how should I allocate them across the path? And the measure that we use is the Fisher information matrix. So it's a estimation problem. Film is a natural thing to use. You know that for unbiased estimator, the CRP uses the bound on the error. So we'll use a film. There are various ways you can use the Fisher. So two different ways people are talking about. So one is what's called A optimal. So basically it's looking at the trace of the Kramer optimal, right? So it's trying to minimize the sum of the variances of the different parameters. And the other one is maximize the determinant of the film, or equivalently minimize the determinant of the CRP. And what that's saying is minimize the volume of the error ellipsoid. And this is a standard thing that we use. And of course, if you believe that some links are more important, you could add link weights to this trace operation. Still. So this is a p-dimensional problem. P is the number of paths. I'm trying to assign fraction of the probes to different paths. So P is at least equal to the number of variables you have, right? That's what inverted solution. So this seems like a hard problem, but at least for these two cases, we have been able to get closed form solutions. We can get, so this is a square case where the number of paths equal the number of links, and of course I'm assuming that my measurements are inverted to begin with. And we know how to do that, what we said so far. Okay, so in this case, I can write explicit expressions for the determinant of the film and for the as far as the trace of the Kramer bond. And then I can find out what the optimal field is. So for B optimal, when I'm trying to minimize the ellipsoid, I need to equal allocation of probes is optimal. For the case where I'm trying to minimize the total variance, so there's a trace operation out here. In this case, the probe allocation is on theta. Right? So here it's independent of theta, so uniform allocation is optimal. Here it depends on theta, of course I don't know theta. So then because you use an iterative approach, you start with uniform allocation, estimate theta, plug it into it, estimate phi, reallocate, and then keep doing that. Okay. So a couple of simulation examples. It says that yeah, it works well. So this is the blue is the uniform placement, and of course if you do the optimal, you get a reduction significant in MSC, it matches the other. In the case of loss tomography, you be a little bit careful because you do have some bias in the beginning, similar and unbiased. So at least in this part, you should use a CR-based pairing. Right? If you have bias estimated, the CR is not the right thing to use different powers. The other two things, this is just saying that if I'm more monitors, then of course I'll do better. More measurements. And this is saying that if I have more paths, I don't necessarily get much improvement. This curves are fairly flat out here, so I don't get much improvement in more paths. And of course, this one still shows you the typical 1 hour and to the number of measurements behavior, which you see in almost all points. So I'll spend 1 more minute on multicast on this additive inventory. So some more work on multicast goes back to Duffield, Towsley, 2000, 2002, and so on. And John was saying earlier, multicast is what you want to do, a broadcast, if you're in a wireless situation. Right? So why is this better? So here, I said once in multicast, the sun went back at the beginning and then at the top, and then all my leaf nodes in the multicast tree receive the packets or don't receive the packets. I can get simultaneous measurement. With unicast, of course, what we're talking about is unicast. I send a probe this way, I send another probe this way, I send another probe this way, and so on. And what the unicast has is that I can control the amount of probes in different paths, which means that may be useful in the area of design, but some things are more important than others. So let me just show you one simulation example. So you looked at binary traits. This is the number of leaves of the tree. So the tree has many nodes. So the blue shows multicast, the red shows unicast. So the larger trees, of course, your estimation gets worse as the tree size increases, and that's clear because the paths become longer and longer. But the other important thing is that multicast is much better than unicast in this case. So you want to do simultaneous. So this was the case where all the rings were, the packet loss probabilities are drawn uniform from point 1 to 1. So what if some rings are very reliable? So reliable meaning that shows them from 0.9 to 1. So packet success probability and loss probability. This is a proportion of reliable rings. And again, the multicast is much better than unicast. And of course, you do better as when you have more reliable links. That's easy to show by measurements. So in general, multicast is better than unicast because so there's also a story for wireless. In other words, you need to take advantage of the wireless. How much more time?
5 minutes.
5 minutes, okay. So I'll spend only a couple of minutes on Boolean tomography. We don't have as much results in Boolean as we have for the additive metric. We have some results, so I'll talk to them. Also, the results are a little bit harder to understand in the Boolean case than in the additive case. The additive case, tree connectivity is the main thing, right? Everything boiled down to showing us something of tree connectivity. So let's look at the Boolean case. So the issue here is the same, right? The path state is normal, if it's normal, all the node states are normal. So here I'm going to look at node failures, not link failure. We do the same for link failure. So path is up, every node is up. If one of the nodes is down, then the path is down. So again, you can set up equations like this. This is this corresponds to the nodes, and this is 0, 1, depending on whether or not that node was on a particular measurement. And this is again whether the path was not proper. So the problem, again, I want to do the same thing. I want to know what the minimum number of monitors required, and for different kinds of failure sets. And the problem is that there's no linear algebra solution to this, right? Having a full rank R does not tell us enough about how to solve this problem. So that's different from the difficulties. So here we look at specific routing assessment, which we did not before. The first one is simplest. So this one, our cap allows you to have cycles. So do whatever you want, right? You can, so long as you don't go over non-existent edges, you can route whichever way you want. The second one is DSP, is where we say, okay, only allowed to have simple paths, no loops. You cannot go to the same vertex twice, or of course not go to the same edge twice. And UP is uncontrollable, which is where the protocol tells you what you can do. So often in many networks, min-hop routing is used, and that's all you can use. You don't have control over, you cannot do source routing. All you can do is what's used. And of course, the UP will be much more difficult than the top one, where any product can do something. So we'll talk about a notion of distinguishable failure set. So what this means is that, can I have measurement? So the idea is very simple. I have two different kinds of failures. can I construct measurement paths so that they have different behaviors on the routine? So for example, a simple case would be, can I distinguish between a node 1 from a node 2? Clearly a path that goes only through node 1, another path that goes only through node 2, then they have distinction. That's a very simple case. Then we also talk about K identifiability, which means that I can identify any set of failures of size K or not. So any set of K nodes that fail, I can distinguish that from any other set of K nodes. So that's important for localization. So most of the time we think K should be 1 or 2, and one fails, 2 nodes fail. Otherwise, it will be something. So we have some results, and of course, as I would expect, these all relate back to K vertex connectivity, since I'm talking about failures of size K. Now, for cap is the simplest, the nested social condition that will say you need K vertex connectivity, and that makes sense. Right? If you don't have K vertex connectivity, then you cannot distinguish between failure sets and non-failure sets. For CSP, that is the one I control the routing.
CSP is the simple part.
The simple part, but you control the routing. So again, you have necessary social condition, but not the same. I have necessary condition and social condition. They're slightly different. They're slightly more onerous than what you have in the cap case. You need K plus 1 and K plus 2 vertex connectivity. So you're expecting more from them. For the case of EP, where I'm given the measurement part, we have a little bit more complex results in terms of MSCD, in terms of number of normal, number of neighbor nodes of monitors, and even eliminating that is the NP half problem plus important. So that's a much more difficult case. But we, again, as I said, we have some points on this. So this one shows you, going back to a question John asked for a different problem, how does density affect monitor placement? So it's because it's a poorly connected networks with more monitors. So here I'm showing you for results for a Hilbert graph with 15 nodes, and these my control parameter out here. The number of nodes is divided 2 times the number of node. So more denser and denser networks out here. And this is what I need, number of monitors I need to distinguish between all one node failures and for all sets of 2 node failures. So of course, if you want to, as my K becomes larger, all the half of the number of monitors I need become larger and larger. That's what we expect. For cap, so cap for one node, I need only one monitor because I cannot article cycles. That's good. The UP of course needs the worst, needs much more, but it's comparable to what we do. So here UP was the min half routing case. So two things of course that nodes are poorly connected, you need more monitors.
But cap is going to give you a lot, you require more.
Cap allows you to have loops.
But it will require a lot more time, right?
It will require more time to because
correct it.
yeah.
There's a trade-off between
There's a
the
trade-off
time
between
detection versus how many monitors you need.
Cap, typically cap will not work unless you can enforce those objects.
Well, I'm surprised that for traditional protocols, the uncontrolled path,
Right.
you need the maximum.
So the third one, yeah, because you have more constraints on what you can do, right? So in simple part,
But you know the protocol.
I know the protocol. So the protocol in this case is min-half routing. Right? So I'm not allowed to use every part.
If you know the protocol, you can use that knowledge to help you figure it out with less monitors. That's my vision, where the failure is.
Oh, okay.
That's why
I'm not sure.
That's why I'm surprised.
Okay.
But if,
But yeah, let's look.
definitely if you have control, you could do better. Right? Because if you control fast,
Right.
I mean, I can go keep it
Yeah,
out.
you can keep going
fine.
fine, yeah.
Like a simple path, I can still control.
But the UP have no control, right? I mean,
Right, but this is the same number for any protocol.
No, sorry. So this is for specific protocol. UP for min-half protocol.
Oh, okay.
Yeah, I mean, we have implements on that. This is a simulation of where we so then you have constraints. I don't know if you can.
Right.
I don't know what kind of things you say for arbitrary, but
Can you compare different uncontrolled paths to see
You always look at remark. So Boolean tomography, in summarize, we have fewer results. It's a much harder problem than the additive case. But again, we know how to monitor placement. We know how to talk about identifiability, which is so first of all, figure out what's the largest number of failures that we can detect. Again, it goes back to figuring out what the connectivity of the graph and keep them different. And monitor placement. So again, fewer results than in the additive case. We don't have the stochastic version yet. There's some old work by Duffy on this. And again, limited resource on this. So just a quick summary slide. So we looked at tomography in the sense of trying to figure out the internals of the network. I know the topology, but I want to know what are the link metrics, whether it's delay or packet loss rate, whether a node is up or down. And we looked at the minimal one replacement problem and a bunch of related problems. The key thing was we had low complexity solutions, so most. In the Boolean case, I didn't stress on that, but figuring out the connectivity of the graph is what n raised to 4 or something like that. So not linear. But at least the additive case very good result. So the other things one could do, which is robust designs, more people that what I talked about. John already a couple of those. So what for real time? It's not that I know the topology, but I can do some topology prediction, and then what can I do? Other thing is what about different Q functions? We talked about simple things, addition, multiplication, Boolean problems, but there may be other things that are interesting. And then of course it goes into group testing. That's what we did. The group constraint here was the instance metric, but you could have other ways of constraining it. There's some connections to group testing that we're not talking about. And of course, we didn't say enough about the real environment, which is one example of multiclass, but that's all I had. This is a lot more